All right, so let's look at the RLC circuit. So here are again, the series RLC circuit. Resistance, inductance, capacitance. Okay. And we saw that V max sine omega t. The current in the circuit as a function of time was given by V max. Z was R squared plus XL minus XC squared sine omega t minus phi. Okay, now let's look at this expression. Okay, the amplitude of the current will be maximum when the denominator is minimum. And there's this term. So you see, if this term went to 0, then the current amplitude would be maximum. So what we are saying is if XL were equal to XC, Z would be minimum. Okay. And so XL is omega L 1 over omega C and omega square equal to 1 over LC, omega equal to, I'm working around that equation, omega is equal to LC. So for a frequency given by, for this particular frequency, if the AC source had this frequency, then the current in this circuit will be maximum. That's what we found. And that's what this diagram is showing you. You see, so omega naught is called that frequency. Omega naught is the frequency where it's the resonance frequency of the circuit. It's equal to 1 over square root of LC. And as you tune the frequency, as you shift the frequency of the source, for omega equal to omega naught, that's 1 omega over omega naught will be 1. The amplitude of the current is maximum. And this is showing you for various values of resistances. And if the resistance is small in the circuit, of course, the current amplitude will be larger. Okay? So an RLC circuit is in resonance when the current amplitude is maximum through that circuit. Okay. And at resonance, at that frequency, you're delivering the maximum power to that circuit as well. Okay. We define the quality factor of a circuit. The quality factor of a circuit is, so here's the frequency, that's the frequency as you're scanning the frequencies. So there's the resonant frequency. The quality factor tells you how sharp this peak is. And see, this is the power delivered to the circuit. Okay. So for frequencies slightly different from resonant frequencies, the power delivered falls off dramatically. And the quality factor is defined as the resonant frequency divided by the width of this peak. Okay, so there's the power at maximum power, and there's half maximum. So the width of the peak is at half maximum. And the reason this is useful is, imagine radios, FM radios and stuff like that. If you have close by stations, if the quality factor is good of your circuit, of your receiver, this would be sharp and you wouldn't catch any disturbance from nearby stations. Okay. Anyway, so the quality factor is how sharp this peak is. And the quality factor is given by omega naught L over R. And so low resistance circuits will have high quality factors. All right, so here's a tuning circuit. So here are various electromagnetic signals, and the way your circuit catches this signal is, okay, what you do is you tune your capacitor such that the frequency of this circuit matches the frequency you're wanting to catch, and when the frequency of your circuit matches the signal you're trying to catch, this signal will set up large amplitude currents. And other signals whose frequency do not match the frequency of your circuit will have low currents in this circuit. Okay, so that's how you tune your circuit. Yeah. Here's a transformer. We've seen these in the last chapter. So you saw that we use transformers all the time. So here's a step-up transformer. Here's a step-down transformer. Here's another step-down transformer. Okay. So step-up transformer, the input voltage is 12 kilovolts, and here in this diagram, the output voltage is 400 kilovolts. Of course, in reality, there are many step-up transformers. Yeah. So the transformer, so here's the input voltage and here's the output voltage. The output voltage is given by N2 divided by N1. N2 is the number of turns there, and N1 is the number of turns here, times the input voltage. Okay. Rectifiers are devices that will convert an AC signal to a DC signal. So here's the simplest rectifier, diode. A diode has a property that it'll let current only through when this end is positive. So for this cycle, the current goes through, and only those two signals, you get a voltage across for those two cycles. These two cycles, the power is wasted. All right, so we'll show you a way to not waste those two cycles. So here is that AC signal, and if you take 4 diodes and connect them like that to the source, now all the cycles are going through. Okay. So now the voltage you'll get across this resistor is that. Okay. So what you have done is you've taken an AC signal and made the negative cycles into positive cycles by using this circuit. So what this circuit has done is converted these negative voltages to positive voltages. Okay, of course, now you don't want to feed this to your MP3 player. What you want is a smooth signal. And so there is that smooth signal, and if you connect a capacitor across your load, the signal gets smoothed out. Okay, so roughly this is the kind of circuit that you, when you plug your laptop to an AC source, you are feeding a 12-volt voltage to your laptop, a smooth signal like that. Now, oftentimes in a wire, what you do is you transmit multiple signals, signals of different frequencies. And then what you need is filters to separate the frequencies. So here's a low pass filter. This device will let only the low frequencies through. The high frequencies will not go through. Remember, the resistance, the impedance of a capacitance was 1 over omega C. So as the frequency increases, the impedance of this guy goes to 0, and if you have 0 impedance, then you don't see any voltage across it. So for high frequencies, you don't see any voltage. So anyway, this device only lets through the low frequencies. So this is a low pass filter. So I don't know if some of you still, if you guys use DSL for internet connection. So DSL is provided by a phone company, and there they use the same wire to send internet data and voice data. Okay. So voice data is or low frequency signals, and internet data is sent over high frequency signals. So this is a low pass filter that separates the internet data from the voice data. And high pass filter is, so for high frequencies, the capacitance, the reactance of the capacitance is almost zero. And those high frequency signals will get through, and that's what you'll see across the load. So here's a high pass filter, which is letting through only high frequency signals. All right, that covers this chapter. So what I'll do is